Hello dear children, welcome to this crash course. The chapter for today's discussion is ray optics and wave optics. Let us first go through the synopsis, recapping of important concepts and revisiting the equations. The basic ideas of geometrical optics are reflection and refraction at plane surfaces and curved surfaces. So this is all about reflection and refraction at plane surfaces and curved surfaces. This is the essence of this entire chapter. So first of all, reflection. Let us consider a plane surface. According to laws of reflection, the incident ray, that is I, and the reflected ray, that is R, and the normal to the point normal at the surface at the point of incidence all lie in the same plane. This is called the plane of incidence. The plane is known as plane of incidence. This plane is plane of incidence, and also known as plane of reflection by the way. And according to laws of reflection, the angle of incidence and angle of reflection are equal to each other. So I is equal to R. Angle of incidence and angle of reflection are equal to each other. Many times this is written in the vector form like this. Suppose E cap represents the unit vector along the direction of incidence, N cap represents the direction of unit vector along normal, and R cap represents the unit vector along the direction of reflected ray. Then R cap is equal to E cap minus 2 times E cap dot N cap N cap. So this is how we represent this idea. And in our current discussion, we consider two main things. One is object and the second is image. Object is said to be real if the rays actually diverge from that particular point, and the object is said to be virtual if the rays appear to converge or they converge. Image is decided by reflected or refracted rays. The point image for a mirror is the point towards which the rays reflect from the mirror or actually converge. That is real image. Or we can say in the case of virtual image, it is that idea from which the reflected rays appear to diverge. So if I consider reflection by a plane mirror, remember the size of the image is same as that of the object. For a real object, the image is virtual, and for a virtual object, the image is real. And also remember, for a fixed incident ray, suppose this is the incident ray and this is the plane mirror, and if the mirror is rotated by an angle theta, then the reflected ray rotates through an angle of 2 theta. It rotates through an angle of 2 theta. One of the very simple concepts, but quite useful in handling problems. Number of images in an inclined mirror, or say number of images in inclined mirrors, or multiple reflections. The idea is like this. First of all, find the value of 360 divided by theta. Let's call this as m. Now if m is even, then number of reflections formed is, number of images formed, is m minus 1 for all positions of object. However, if m is odd, then n is equal to m if the object is not on the bisector, and if m is, for the same case, n is equal to m minus 1 if the object is on the bisector. So the trick is to get the value of m. What is that m? 360 by theta. And if m is even, then n is equal to, that is the number of images formed is m minus 1 for any position of the object. And if this turns out to be odd, then n is equal to m if the object is on the bisector, otherwise it is m minus 1. And if m is fraction, suppose I consider m to be a fraction, then you may ask, what about this one? Then n is the nearest even number. N is the nearest even number. Suppose I consider the idea of paraxial rays. You know, paraxial rays are the rays which form very small angle with the axis. These are called paraxial rays. And all the formulae that we discuss here are applicable for paraxial rays only. Here, in order to discuss all those things, the sign convention that is followed is something like this. It's basically Cartesian sign convention, according to which the pole is at the origin and the direction of the incident ray is taken as positive. Direction of incident ray is taken with positive sign, positive x-axis, and vertically up positive y-axis if it is along the incident direction. And all the distances are measured from the pole. So what is your reference line? Reference point is the pole. Suppose I consider, in this case, a spherical mirror. You know, spherical mirror is basically a cutout portion of a sphere. For example, if I consider something like this, I can cut out this portion, I can silver this portion, and this is your C, center of curvature, and this is your focal point F, and this is M dash, which is the mirror, and this is what is known as concave mirror. Here the ray of light can be shown to be incident like this. Likewise, a convex mirror can be shown like this. This is C, and here is the focal point, and a ray of light which is incident like this appears to bend towards focal point, and it actually eventually gets reflected like this. This is your incident ray, this is reflected ray, incident ray is here, the reflected ray is here. This is a convex mirror, a convex mirror. And remember, the radius of curvature and the focus of concave mirror, so radius of curvature and the focus, or say focal length, are taken with negative sign, and for a convex lens, R and F are taken with positive sign. They are taken with positive sign. Mirror formula relates the object distance and the image distance to the focal length. F is the x coordinate of the focus, U is the x coordinate of the object, and V is the x coordinate of the image. We call it as object distance, image distance, and the focal length. The transverse magnification is given by H2 divided by H1 or Hi divided by Ho. This can also be written as minus V divided by U, where V is the image distance and U is the object distance. And remember, these are measured perpendicular to the principal axis of the mirror. And the longitudinal magnification is given by M, we can call it as ML, and this is length of the image divided by length of the object. Length of the image divided by length of the object. And for small objects, ML is equal to minus M square, where M is the transverse magnification. If I consider a spherical mirror, for example, the representation can be like this. Let's assume that an object is traveling along this direction, and velocity of the image needs to be found out. Let's assume that the object is moving along this direction and the image velocity has to be found out. So, velocity of the image of a moving object. So, object is moving now. In this case, the object is coming from infinite or infinity towards the focus of the concave mirror. So, I can write 1 by U plus 1 by V is equal to 1 by F. Or I can write minus 1 by, I can differentiate it with respect to T. So, I will get 1 minus 1 by U square du by dt minus 1 by V square dV by dt is equal to 0, or velocity of the image is equal to minus V square by U square velocity of the object. Velocity of the object. So, this can also be written like this, minus M square velocity of the object. So, this is velocity of the image with respect to mirror, and this is velocity of the object with respect to mirror. That is du by dt. This part is du by dt, the left hand side is dv divided by dt. If I consider a spherical mirror, or say a mirror, then its optical power is given by minus 1 by f, measured in diopters, of course. So, in diopters, the optical power of a mirror is the reciprocal of its focal length, with a negative sign, of course. So, let us consider the idea of refraction, of course, at plane surfaces and then curved surfaces. So, the laws are like this. First of all, laws of refraction. Again, if I consider is an interface on which light is incident, this is the normal, and the ray of light gets refracted inside the medium, r being the angle of incidence, I being the angle of incidence, and r being the angle of refraction, n1 and n2 being the respective refractive indices. And n cap is the unit vector along the normal. then first of all the incident ray, the refracted ray and the normal all lie in the same plane. That's the basic idea. And the same thing can also be written in this form: E cap cross n cap dot r cap is equal to 0. What is that E cap? Unit vector along the direction of incident ray. R cap is the unit vector along the direction of the refracted ray, and n cap is the direction or unit vector along the direction of the normal drawn at that point. Another law which is quite useful is Snell's law, according to which n1 sin I1 is equal to n2 sin r. N1 sin I is equal to n2 sin r. Or we can write sin I divided by sin r is equal to n2 by n1, that is refractive index of the second medium with respect to that of the first medium. This is also written as 1 n2. And this 1 n2, which is n2 by n1, happens to be the ratio of the speeds as given by this equation. n2 by n1 is equal to v1 by v2, or this is also equal to lambda 1 by lambda 2. Actually, this is written in the vector form like this: n1 refractive index mod of E cross n is equal to n2 mod of r cross n. Remember this vector representation of Snell's law. Also remember that during refraction there is no change in the frequency of the light. During refraction, the ray of light undergoes a change in its path. There is a deviation. So this is the direction of the refracted ray. See, I is the angle of incidence and r is the angle of refraction. Then this is the deviation. The deviation is given by I minus r. So whenever a ray of light undergoes a change in the path, the deviation from its current path, actual path, is given by delta is equal to I minus r. If I consider such a refraction to take place from a parallel sided block, a parallel sided slab or block, then what exactly happens? Let us see. The ray of light is incident here, it undergoes refraction, and it is now it has actually traveled from rarer to denser medium, therefore it moves towards the normal, and then it gets out traveling from denser to rarer medium, therefore it moves away from the normal. But clearly the incident ray and the emergent ray are parallel to each other. Thus there is a shift in its position, and this is what is called as lateral shift. There is a shift in its position, or say there is a shift in its path. This is what is called as lateral shift. Let T be the thickness, I be the angle of incidence here, and R be the angle of refraction at the first surface. This is same as I here, right? This is same as I. Thus, if I consider the lateral shift as some x, or say L, then that lateral shift T is given by, or say x given by, lateral shift x is given by T into sine of I minus r divided by cos r, where T is the thickness of the slab. T is the thickness of the slab. Remember, the emergent ray will not be parallel to the incident ray if the medium on both the sides are different. The requirement is that this medium and this medium should be same. They should have the same refractive index. Likewise, if a ray of light travels from one medium to another medium, then it gives rise to an apparent change in the position of an object. For example, imagine that an object which is placed inside this medium is viewed from this medium. Let us see what happens. So this is a ray of light starting from the object and it eventually reaches the observer here. So this is the eye position. This is where the observer is present. But the observer perceives the object to be here. The observer perceives the object to be here. He perceives it to be at a depth of some h dash. Even though the actual depth is h, he perceives it to be at a depth of h. Let's assume that the refractive indices are n1 and n2 here, and assume that n1 is greater than n2. Then for a near normal incidence, h dash is given by n2 by n1 into h. n2 by n1 into h. So there is a shift in the position, and this is known as apparent depth. So he looks at the object and tells that it is at this depth. So there is an apparent shift also. There is an apparent shift. What is that apparent shift? Delta h. Clearly that delta h is equal to h dash minus h, or h minus h dash, and that is equal to t into 1 minus 1 by n. What is that t? T is the thickness of the slab. For example, here if I look at it, then you can consider it like this. T is the thickness here and refractive index is 1 here. It's viewed from here, and the object is located here, and it travels like this, and eventually it comes out like this. So the reported position is here, and this is the apparent shift. This is the apparent shift. Even though the object is here, it is perceived to be here. So that shift in the position, what is called as apparent shift, is given by delta h, which is t into 1 minus 1 by n. Remember, the apparent shift is always along the direction of the incident ray, and h and h dash are always measured from the surface in such cases. Another important concept of refraction at plane surfaces is the idea of critical angle and total internal reflection. If a ray of light is incident at various angles, we notice that the ray of light gets refracted at various angles of refraction. For example, this is one. And if I change the angle of incidence, notice that the angle of incidence is here, and I'm increasing the angle of incidence, and it starts getting towards the normal, so towards the interface. Now for a particular position called as C, the refracted ray just grazes the surface, and this angle of incidence is in the denser medium, while the ray tries to get out into the rarer medium, is called as critical angle, and this phenomenon is known as total internal reflection. If I increase the angle of incidence further, then the incident ray eventually gets reflected inside the same medium. This is what is called as total internal reflection. In order that the total internal reflection takes place, remember, the light should be traveling from denser to rarer medium. This is one of the very important requirements. And the angle of incidence should be greater than the critical angle. This critical angle C is given by sine inverse refractive index of the rarer medium divided by that of the denser medium. This can also be written like this: sine inverse speed of the denser medium divided by speed of the rarer medium. Or this can also be written as sine inverse wavelength of the denser medium divided by wavelength of the rarer medium. Any of these representations is perfectly fine as far as critical angle is concerned. Another important application of all these concepts is refraction through a prism. Let's consider a prism. This is the base of the prism. P, Q and R is the angle of the prism. Let us consider a ray of light incident here, and this is the angle of incidence I, and it gets refracted, so I can show the refraction like this, and this is the angle of refraction here, R. It should have actually traveled along this direction, and it is incident here, and it gets out like this. This is R dash and this is I dash, and it tries to get out like this, and this is the final emergent rays direction, and this is the deviation delta. The deviation delta is given by I plus I dash minus R plus R dash. And also remember, R plus R dash is equal to A. R plus R dash is equal to A. So remember this one. And if you plot the variation of deviation versus the angle of incidence I, then the graph is something like this. Something like this. This corresponds to delta max, this corresponds to delta minimum, and this corresponds to I minimum, this corresponds to I is equal to E, and this corresponds to I is equal to E max, and this is E is equal to 90. So the nature of the graph is of this form. So if you notice, there is one particular angle of incidence for which the angle of deviation is minimum. That means for this delta minimum, for delta to become minimum, we have I is equal to I dash and R is equal to R dash. So when it happens, the ray of light travels symmetrically about the prism like this, and in such a case the refractive index is given by sine n is equal to sine of A plus delta minimum divided by 2 whole divided by sine of A by 2, where n is the refractive index of the medium, or say absolute refractive index of the medium. If I consider such a thin prism, for a thin prism, deviation can straight away be written as delta is equal to n minus 1 into A. N minus 1 into A. Refraction through spherical surface. Refraction through spherical surface. Let us consider a spherical surface like this, and this medium is of refractive index n1, this is of refractive index n2, and this is the pole, and here is the center of curvature, and this is object position. So I'll show an approximate representation. The center of curvature is here. So this is the representation. And remember, the equation for refraction at a spherical surface is given like this: n2 divided by v minus n1 divided by u is equal to n2 minus n1 divided by r. And v, u and r to be kept with the sign like this. Remember, the radius of curvature is here from this point to this point, and in such a case the magnification is given by n1 by n2 into v divided by u. One of the important applications is lens formula. Suppose I consider a lens. This is medium 1. This is also medium 1. Refractive index is n. And this is the positive direction. Then the equation correspondingly is 1 by v minus 1 by u is equal to 1 by f. And in general, we can write 1 by f is equal to n minus 1 into 1 by r1 plus 1 by r2, where r1 and r2 are the radii of curvature of the different surfaces. You may also write m is equal to v by u in general as the magnification. Suppose I consider two such lenses connected. For example, there are two such lenses kept next to each other. Their focal lengths are f1 and f2. Then the power of the combination is given by p1 plus p2, that is 1 by f1 plus 1 by f2. That's the power of the combination. While solving the problems, you need to use the appropriate sign convention. Appropriate sign convention is to be used to solve the problem here. Suppose we consider silvering of one surface of a lens. For example, this is the construction. Let's assume that this surface is silvered. Now, if the plane surface is silvered, then the focal length is given by r divided by 2 times n minus 1. Focal length is given by r by 2 times n minus 1. And if the convex surface is silvered, for example, let me draw the diagram like this. Then the focal length is given by r by 2n. r by 2n. And you can use the equation P equivalent is equal to 2p plus P due to mirror. P due to lens plus P due to mirror. So this equation can be used to solve the problem as far as these ideas are concerned. So these are some important concepts as far as ray optics is concerned. Let us take up the discussion of wave optics. The basic idea of wave optics involves interference and diffraction. In order to understand them, we consider the following ideas. The idea of coherent sources. What are coherent sources? Two sources are said to be coherent if they produce waves of same frequency and hence wavelength and constant initial phase difference. They are known as coherent sources. Two sources are said to be incoherent if they have different frequency and initial phase difference is also not constant. As I said, the important applications are in the form of interference, particularly Young's double-slit experiment. During interference, the intensity of the resultant wave for coherent sources is given by I is equal to I1 plus I2 plus 2 root I1 I2 into cos phi naught. That is the resultant intensity. Remember, this is for coherent sources. If we consider incoherent sources, then the intensity is given by I1 plus I2. And remember, intensity is directly proportional to the width of the slit width. And this is directly proportional to amplitude square. So we can write it like this: I1 by I2 is equal to W1 by W2 is equal to A1 square by A2 square. Using this concept, we can find out what the maximum intensity is and what the minimum intensity is. In fact, the ratio can be found out like this: root I1 plus root I2 whole square divided by root I1 minus root I2 whole square. And this can be simplified further: A1 plus A2 whole square divided by A1 minus A2 whole square. So these are some generic equations as far as interference is considered. In the case of Young's double slit experiment, is the construction. This sends the first slit sends the light along this direction, and the second sends the light along this direction to produce interference. D is the slit width, and for small angle I can see this happens to be d sine theta. D sine theta approximately equal to theta, approximately d sine theta approximately equal to d theta, approximately equal to d tan theta. Let us consider a couple of important equations here. Number one, distance of nth bright fringe xn is equal to n lambda d divided by d. Path difference is equal to n lambda, where n is equal to 0, 1, 2, 3, 4, etc. for constructive interference or bright fringe. Likewise, distance of nth, or say mth, we will call mth dark fringe xn is given by 2m plus 1 lambda d divided by 2d, and the condition is path difference is equal to 2m plus 1 lambda d divided by d. (2m plus 1 lambda by 2). That is the path difference. Where m is equal to 0, 1, 2, 3, 4, etc. And this is, remember, this is for destructive interference to take place or dark fringe, for dark fringe. The separation between the fringes, or say successive fringes, known as fringe width beta, is lambda d divided by d, and the angular fringe width is equal to beta by d, which is lambda divided by d. Suppose a transparent sheet is introduced along an interfering wave. Assume that its thickness is t, refractive index is n. then the fringe is displaced by this distance d into n minus 1 into t divided by d. This can also be written as beta divided by lambda into n minus 1 into t. And it is shifted towards the side in which the sheet is introduced. But the fringe width, remember, remains the same. There is no change in the fringe width. There is no change in the fringe width. One of the important types of questions which is frequently asked is what happens if the interference experiment is repeated with bichromatic light. That means two wavelengths. Then the fringes of the two wavelengths will be coincident. So in the case of bichromatic light, then for coinciding first time, we have n into beta of the longer is equal to n plus 1 into beta of the shorter. That means the minimum value of n for which the the fringes coincide is given by n into beta of the longer is equal to n plus 1 into beta of the shorter. Sometimes in the questions he asks, if the maximum number of maxima or say minima are asked in the question, here maximum number of maxima means maximum number of bright fringes or say dark fringes are asked in the question. So use the fact that value of sin theta or cos theta can't be greater than 1. For example, if I consider n max, this is d by lambda. So total number of maxima corresponds to 2 into n max plus 1. Very simple idea. Diffraction. In Fraunhofer diffraction, for minima, a sin theta is equal to n lambda, and for maxima, a sin theta is equal to 2n plus 1 into lambda by 2. A sin theta is equal to 2n plus 1 into lambda by 2. And the linear width of central maxima, that is W, is equal to 2 lambda d divided by A. And the angular width of central maxima is given by WE, I'll call. This is equal to 2 lambda divided by A. So these are some important equations as far as diffraction phenomenon is concerned. In our next session, we are going to take up numerical problems based on these concepts. Let's discuss numerical problems based on ray optics and wave optics. Question number 1. An equiconvex lens is cut into two halves along XOX dash and YOY dash as shown. Let F, F dash and F double dash be the focal lengths of the complete lengths of each half in case 1, 2 and 3. 1, 2. Choose the correct statement from the following. Now, in the first case, it is kept like this, and in the second case, it is kept like this. It is cut like this. In the horizontal cutting, F dash is equal to F, because R1 and R2 do not change. While in this case, F double dash becomes 2F, because R1 or R2, any one of them becomes 0. Thus, f dash is equal to f, while f double dash is equal to 2f. D is the correct choice. Example 2. The size of the image of an object which is at infinity as found by a convex lens of focal length 30 cm is 2 cm. If a concave lens of focal length 20 cm is placed between the convex lens and the image at a distance of 26 cm from the convex lens, calculate the new size of the image. Okay, let's show the construction. Similarly, here and this is 26 centimeter and this is 4 centimeter, right? So, I will write 1 by f is equal to minus 1 by u plus 1 by v. That gives me 1 by v is equal to 1 by f plus 1 by u minus 1 by 20 plus 1 by 4 gives me 1 by 5. Therefore, v is equal to 5. Now, for concave lens, what do we have? Height of the image by height of the object is equal to v divided by u modulus 5 divided by 4, or height of the image is equal to 2 times 5 divided by 4, that is 2.5 centimeter. So, the new size of the image is going to be 2.5 centimeter. Example 3. The refractive index of the material of a prism is √2 and its refracting angle is 30 degree. One of the refracting surfaces of the prism is made a mirror inwards. A beam of monochromatic light entering the prism from the other face will retrace its path after reflection from the mirrored surface if its angle of incidence on the prism is. So, construction. This I and this is 30 degree. So, now n is equal to sin I divided by sin r, or sin I is equal to n sin r. So, √2 sin 30, that is equal to 1 by √2. So, sin I is equal to 1 by √2 implies I is equal to 45 degree. Therefore, the angle of incidence on the prism is I is equal to 45 degree. Example 4. In order to obtain a real image of magnification 2 using a converging lens of focal length 20 centimeter, where should an object be placed? Simple thing. So, you need to find out u. So, I have m is equal to minus v by u, give me minus f divided by u plus f, that is minus 20 divided by u plus 20, or 2 is equal to minus 20 divided by u plus 20, that gives me u is equal to minus 30 centimeter. So, where should it be placed? At a distance of minus 30 centimeter. Example 5. A telescope has objective lens of focal length 200 centimeter and eyepiece of focal length 2 centimeter. If this telescope is used to see a 50-meter tall building at a distance of 2 km, what is the height of the building formed by the objective lens? Okay. So, 1 by f naught is equal to 1 by u naught plus 1 by v naught, giving me 1 by 2 is equal to 1 by V naught minus 1 by 2000. That is 2 kilometers. That gives me V naught is equal to 2000 divided by 1001, and I can take it as 2. Now, magnification of the objective is equal to I divided by O, that is V naught divided by U naught. That gives me the image size as V naught by U naught into O, that is 50 into 2 divided by 2000 is equal to 0.05 meter, or the height of the image formed by the objective lens is 5 centimeter. This is our correct choice. Example 6. A convex and a concave lens, each having same focal length of 25 centimeter, are put in contact to form a combination of lenses. The power in diopters of the combination is. So 1 by F is equal to 1 by F1 plus 1 by F2 when in contact, 1 by 25 minus 1 by 25, as one is convex and the other is concave. So this is 0, and therefore the power, which is reciprocal of focal length, is 1 by infinity. Why infinity? 1 by F is 0, so F is equal to infinity, that is nothing but 0. So the power is 0. Example 7. A convex lens of crown glass of refractive index 1.525 will behave as a divergent lens if it is immersed in. Clearly, in order that it behaves like a divergent lens, it should be immersed in a medium of higher refractive index. That's right. So higher refractive index corresponds to carbon disulfide, whose value is 1.66. So A should be our correct choice. Example 8. A convex lens of focal length 0.5 meter and concave lens of focal length 1 meter are combined. The power of the resulting lens will be, okay. So again, 1 by F is equal to 1 by F1 plus 1 by F2. So 1 by F is equal to 1 by 0.5 plus 1 by minus 1. That gives us F is equal to 1 by F is equal to 1, or power is equal to 1 by F, that is nothing but 1 diopter. So the power of the lens is 1 diopter. The power of the resulting lens is 1 diopter. Example 9. A person cannot see object clearly beyond 2 meters. The power of the lens required to correct his vision will be, what is it? So for u is equal to infinity, v is equal to minus 2 meters. You can't see it beyond 2 meters, means v is equal to minus 2 meters. So I'll write 1 by f is equal to 1 by v minus 1 by u. That gives me minus 1 by 2 minus 1 by infinity minus 1 by 2. So f is equal to minus 2, or the power is equal to, what is the power equal to? Power is 1 by f, which is minus 1 by 2, or this is nothing but 0.5 diopter with a negative sign. Example 10. Critical angle of glass is theta 1 and that of water is theta 2. the critical angle for water and glass surface would be. Refractive indices are given. So we have sin theta 1 is equal to 1 by ng, sin theta 2 is 1 by n of water. As ng is greater than n of water, theta 1 is less than theta 2, or critical angle theta 1 is less than theta 2. So critical angle theta between glass and water is given by, what is that? Sin theta is equal to nw by ng, or theta should be greater than theta 2. So theta should be greater than theta 2. That means it is option C. Few questions based on wave optics. If light of low wavelength is used in Young's double slit experiment, then the width of the fringe will be. So now beta is equal to given by n lambda, that is lambda d divided by d. Now if the wavelength decreases, the fringe width decreases. So as the wavelength of the light used decreases, the fringe width also decreases. A is the correct choice. Example 12. If a torch is used in place of monochromatic light in Young's double slit experiment, what will happen? Fringe will appear for a moment and then it will disappear. Fringes will occur as from monochromatic light. Only bright fringes will appear. No fringes will appear. So what happens here? If we use torch light in the place of monochromatic light, then overlapping of fringe patterns takes place, because it contains wavelength, or say light of all wavelengths, then overlapping takes place. Overlapping takes place means fringes cannot be seen distinctly, or we can say no fringes will appear. It is a continuous band. D is our correct choice. 13. Two parallel slits 0.6 mm apart are illuminated by light source of wavelength 6000 angstrom. The distance between the consecutive dark fringes on a screen 1 meter away from the slits is. Alright. The distance between two consecutive dark fringes x is given by lambda d divided by d. It is equal to fringe width. So 6000 into 10 to the power of minus 10 into 1 whole divided by 0.6 into 10 to the power of minus 3. That is 1 into 10 to the power of minus 3 meter, or 1 millimeter. So the successive dark fringes are separated by this distance, 1 millimeter. 14. If a transparent medium of refractive index mu is equal to 1.5 and thickness T is equal to 2.5 into 10 to the power of minus 5 meter is inserted in front of one of the slits of Young's double slit experiment, how much will be the shift in the interference pattern? The distance between the slits is 0.5 mm and that between the slits and the screen is 100 centimeter. So the shift delta x is given by n minus 1 into t into d divided by d. 1.5 minus 1 into t, 2.5 into 10 to the power of minus 5 into 100 into 10 to the power of minus 2 whole divided by 0.5 into 10 to the power of minus 3. And it simplifies to 2.5 centimeter. So 2.5 centimeter is the shift. Example 15. In Young's experiment, monochromatic light is used to illuminate the two slits A and B. Interference fringes are observed on a screen placed in front of the slits. Now, if a thin glass plate is placed normally in the path of the beam coming from the slit, what happens? The fringes will disappear, the fringe width will change, the fringe width will increase. There will be no change in the fringe width. So here, in the presence of a thin glass plate, the fringe pattern shifts. The fringe pattern shifts, but there is no change in the fringe width. The fringe width remains the same, but there will be there will be a shift in the position. So there will be no change in the fringe width, and there will be a shift. Example 16. If two waves represented by y1 is equal to 4 sine omega and y2 is equal to sine omega t plus pi by 3, 4 sine omega t, and y2 is equal to sine omega t plus pi by 3, interfere at a point, the amplitude of the resulting wave. Okay. So clearly notice that in this case, the phase difference is pi by 3. The first wave is of amplitude 4 and the second wave is of amplitude 1, correct? And the resultant amplitude is given by square root of a square a1 square plus a2 square plus 2a1 a2 cos phi, root of 16 plus 1 plus 2 into 4 into 1 into cos pi by 3, cos 60 is 1 by 2. So this turns out to be root of 17 plus 4, that is root 21 is the answer. So root 21 is the answer. Next one. In a wave, the path difference corresponding to a phase difference of phi is. Suppose I consider a wave represented like this. This corresponds to one wavelength. And this also corresponds to the projection of the circle over one particular circle, or say one complete oscillation or one complete circular journey. The angle covered is 2 pi. The angle covered is 2 pi. Thus, how are they related? If I consider, say, any two positions having a path difference of delta x, assume that the phase difference between those two is delta phi. So lambda corresponds to 2 pi, delta x corresponds to delta phi. So we can relate them. Delta x is equal to lambda by 2 pi into delta phi. C is our correct choice. 18. In Young's double slit experiment, if the width of the slits are in the ratio 4:9, the ratio of the intensity at maximum to intensity at minima is. So slit width ratio is 4:9. Therefore, I1 is to I2 is equal to 4:9. Or A1 is to A2 is equal to 2:3. Therefore, now we have I max to I minimum given by A1 plus A2 whole square divided by A1 minus A2 whole square, or this is 2 plus 3 square, 2 minus 3 whole square, or this is 25:1. So C is our correct choice. Example 19. An interference pattern was made by using red light. If the red light changes with blue light, the fringe will become. Okay. So you notice that the fringe width is given by lambda d divided by d. That means fringe width is directly proportional to lambda. Now, as the wavelength has decreased, the fringe width decreases, or the fringes become narrower. B is our correct choice. Example 20. Two beams of light having intensities I1 and I2, I1 and 4, that is I and 4I, interfere to produce a fringe pattern on a screen. The phase difference between the beams is pi by 2 at point A and pi at point B. Then the difference between the resultant intensities at A and B is. Okay. So here I1, that is at at A, IA is I1 plus I2, that is phi A, phi I. And at B, IB is equal to I1 plus I2 plus 2 root I1 I2 into cos pi. So this is going to be 5I minus 4I, that's nothing but I. Then the difference between their intensities, IA difference IB is equal to 5I minus I, that is 4I. The difference between their intensities is 4I. B is our correct choice. So with that problem, we have come to the end of this session.